standing in for David today, who's out for business, and I have the pleasure of introducing Professor Phil First. Dr. First is a professor in the School of Physics. He got his undergraduate degree from the University of Wisconsin, his graduate degree from the University of Illinois in 1988. He's been a faculty member here since 1990. I actually had him as one of my professors in my undergrad time here at Tech. Since then, he's made some fundamental contributions. So his work, is in the field of surfaces, interfaces, and nanostructures. He's made some integral contributions to the work in graphene and on epitaxial graphene, on silicon carbide, and lower dimensional materials. And he is the founding chair of the AES, is it conference or group on?
Just one of the divisions.
Divisions on nanostructures and interfaces. And right. So he's here today to talk to us about new semiconductor or new materials for nanoelectronics.
Just read it off the slide.
Yeah, I can do that. So and then a view from the bottom. So with that,
thank you, Walter. Sorry for the few technical difficulties that OIT imposed on us. So I'm here to tell you a little bit about new materials for nanoelectronics. And I am certainly not, I'm not the world's expert on this, that's for darn sure. This is, in fact, the first time I will have talked about topological materials, and we'll see how it goes. Anyway. Some of you may recognize this slide from a number of years ago, which came from Intel and UC Berkeley, that sort of characterizes the problem with electronics these days, and that is power. So for many years, we followed Moore's law in scaling down the number of transistors on the chip and the size of the transistors. And in the end, it turns out that we didn't hit that wall for scaling the size as quickly as we hit the wall for power. So if you look back in 2008 was about when things really came to a head, and then the power density on the chip was about equivalent to that of a rocket nozzle. So you have to figure out ways to get rid of that power or do things at lower power, and you may recall that it was around this time that you really started seeing multi-core CPUs, GPU processing, anything to parallelize things so that you didn't have to have one CPU doing all the work. So one of the solutions that was bandied around for a long time involved carbon and nanotubes and graphene. So graphene, you probably are aware, is just a sheet of carbon atoms, single sheet of carbon atoms in the plane. They are sp2 bonded. That's these bonds sticking off over here. But sticking out of the plane, there's a p orbital, the pz orbital, which I'll remind you has a phase. It's positive phase over here, negative phase over there, or vice versa, okay? And in fact, the electronic properties near the Fermi level are determined by the bands that are formed by overlap, that's pi band overlap, of these pz orbitals on each one of these sites. Now, there are two identical atoms in the unit cell that I've colored red and blue here. They're identical, except that they're related by an inversion. That is, if you look at the sense of the bonds around the blue atom, they're 180 degrees rotated, or mirror symmetry of the bonds around the red atom. Okay, so that's the only thing that distinguishes them is their bond symmetry around them. So graphene, graphene you might see was discovered in 1947 by Phil Wallace. Well, okay, he did calculations based on a single sheet of carbon atoms, and he came up with an energy structure. This is a two-dimensional energy versus momentum. Well, it's crystal momentum. If you multiply by h bar, you get essentially a momentum. So this is energy as a function of momentum in kx and ky directions. And what you find are these interesting regions where you get two cones intersecting at a point. That point is known as the Dirac point. And in fact, for graphene, that's where the charge neutrality point is. That is, all the bands are filled up to this point, the Dirac point, and then they're empty above that point. But you can dope graphene. You can put extra electrons in or take electrons out so that the Fermi level could be above or below the Dirac point. But for neutral graphene, it's right at the Dirac point. And these bands, based on the tight binding model, aren't, in fact, have an analytic form. The important part for much of what we do is down here, right around the Dirac point. And if you actually look at the wave functions here as a function of momentum, so consider the wave functions as being either pi bonding between two neighboring atoms, A and B, or pi anti-bonding between two neighboring atoms. That just, they're in phase or out of phase, okay? And then if I multiply those wave functions by 1 at every site, then up here I will have the anti-bonding version of the periodic wave function, and here I have the bonding version of this periodic wave function, where all these things are in phase. Up here we alternate plus minus, okay? Just where that plus minus is the phase of the wave function. So if I go to a different momentum, what happens is that these wave functions get multiplied by a phase factor, a complex phase factor, e to the I k dot r. And if you look at some high symmetry points like the M point, then what you'll find is that I have a wavelength that's determined by the k vector, just by de Broglie's relation, right? Is P is h over lambda, and k is h bar k is equal to P. So lambda is square root of 3a here, and you can see that along any given wavefront here, all of these things are in phase. Whereas if I go to the higher energy side, that's up here, then I alternate in plus minus along a wavefront. Okay, so that makes this higher energy than that one, which is why you get the gap at the M point. But if you go to the K point, then what you'll find is that multiplying this by the correct phase factor, I get a wave function that looks something like this, which is I get a maximum here, I get some sort of minor maxima over there. These are all on the A sites, let's say. Whereas over here I get exactly the same wave function, but those maxima occur on the B sites. Well, those are identical in energy. It's just shifting the wave function by from A site to B site, but there was nothing to really distinguish them. And so these two things are degenerate in energy, and that's why at the K point we have this degeneracy between what the bands that came from the anti-bonding states and the bands that came from the bonding states. Now the consequence of that, one of the consequences is that if I try to have an electron backscatter, so this is a blow up near the Dirac point of the energy versus wave vector, okay? And those Dirac points in K space, they're curiously given the nomenclature of K, where that's a capital K to distinguish it from the wave vector, little k. So in the vicinity of this K point where the cones meet, if I look at the sense of the wave functions, well, over here, it is the bonding wave function that dominates over here, whereas it's the anti-bonding wave function that dominates over there. This circle is a constant energy circle in the vicinity of the Dirac point. Okay, so if I want to reverse the direction of current flow, let's say, so I have an electron propagating in the positive x direction. You remember that the direction of that the electron goes is the group velocity. That's the slope of this cone. And so to reverse the group velocity, I go to opposite slope. That's over here. A backscattering event would have to flip the sense of bonding and anti-bonding. Now, we call that the amount of bonding versus the amount of anti-bonding. We characterize that by a pseudospin. Okay, you can look at that as the pseudospin characterizing the relative phase between the wave functions on each of the sublattices A and B. So this scattering from here to there, which is a small wave vector that would correspond to scattering from something that is physically a fairly large size, it actually can't be done because I would have to flip the pseudospin. Physically, what that means is I would have to take bonding type orbitals and dump them into an anti-bonding configuration, and that's just really hard to do. You can do it if you have a large wave vector, which is something that's determined by small structure things, so you can transfer lots of momentum. In that case, I can get a scattering all the way across the Brillouin zone of the material, and I can get some backscattering in that case, but only if I have structures that are on the atomic scale. They're the only ones that can provide that large momentum transfer. So the good thing about graphene was that it inhibited backscattering of the electrons or holes as carriers. The inhibited backscattering means I get closer to dissipationless transport in the plane, right? Which is a great thing if you're considering power for devices. So graphene was great from that aspect, but it wasn't truly protected. I could still get backscattering. These states propagating in this positive x direction, they're not really protected completely from backscattering. And in fact, I could backscatter to other angles with some probability. So it was thought that this was good for electronics because we could potentially have perhaps ballistic transport, and in fact, Walt DeHeer's group has recently shown really ballistic transport in one-dimensional wires. High current density, because these carbon materials are incredibly tough as far as heating up and handling that high current density. The doping can be done by applying an electric field. That's gate doping. And the configuration, because it's so thin, is very, very good as far as the capacitance is concerned. And capacitors are a problem because when you're switching devices, you're always having to charge up capacitors, and that's where a lot of the power is going, is from the transistors driving that charge onto the capacitors. So this concept of nanotube electronics was very hot in the early 2000s, and this was sort of a man of the year sort of thing, but material of the year, I don't know, from science. And the concept was nanotube electronics. You haven't seen that yet in your CPUs. Walt DeHeer, Claire Berger, and I participated a bit. We had the concept to go to graphene-based electronics, where instead of nanotubes acting as waveguides for electrons, instead you would have lithographically patterned lines of a particular width acting as the waveguides for electrons. The only difference, the most fundamental difference, being simply the boundary conditions, hard walls for the ribbons versus azimuthal wave function continuity for the nanotubes. Okay. And so we laid this out with the bold title of ultra-thin epitaxial graphite, 2D electron gas properties, and a route toward graphene-based nanoelectronics. It is a long route, but there have been a number of successes. I don't have time to go into them. What I'd like to do is look beyond graphene, because I think this is really sort of, as I think I said in the abstract, is kind of a mini revolution in condensed matter physics at the moment, which is the role of topology in the electronic structure of a material. And let me just give you a couple of nutshell things. That is, in a topological insulator, we have pseudospin becoming real spin. And the backscattering protection is therefore much stronger because it's hard to flip a magnetic moment. Okay? It requires angular momentum, not just plain old momentum. The 2 Dirac cones become 1 Dirac cone. Removing that degeneracy removes another route for backscattering. That's a good thing. So, what is an insulator? An insulator is something with a band gap, you would say. Well, that is for, up until at least the 1980s, that's pretty much what people thought. And so you would have an insulating state that was a consequence of quantization that was due to the Coulomb potential of due to the nuclei in materials. Now, in the 1980s, early 1980s, there was discovered the quantum Hall effect, the integer quantum Hall effect. And in that case, you have quantization of these orbits not due to an electric field, but due to a magnetic field. Now, a magnetic field breaks time reversal symmetry, which changes some things. And you nevertheless have gaps. These gaps are due to quantization with 1 wavelength, 2 wavelengths, 3 wavelengths around the circumference, at least semi-classically. But this is not, it turns out that this state is not just the same as an insulating state. And you may have noticed the Nobel Prize this year, one of the members of the Swedish National Academy was showing things like this because the Nobel Prize was given to Thouless, Kosterlitz, and Haldane for their work in understanding the topology of, in particular, the quantum Hall state. And what they showed, Thouless and Kosterlitz, was that the quantum Hall state was not the same as a normal insulator, in the sense that a sphere and a donut are topologically distinct by virtue of this having a hole in it. Okay, so how are they different? Well, and what are the consequences? If I look at a quantum Hall state, which has a band gap between these discrete levels, and I now connect it to an insulator, like vacuum. Vacuum is a good insulator. In fact, you really can look at vacuum as being a semiconductor with empty states, which are normal particles and electrons, and filled states, where if we take a particle from the filled state, we leave a hole that's a positron to an electron. They're antiparticles, just like electron and holes in a semiconductor. Okay? So if I connect the quantum Hall state to an insulating state, the quantum Hall state is different, and topologically it's characterized by a number, a topological invariant that basically says that the donut has a hole, and the insulator is a sphere. Now I have to connect these two, and what happens for the quantum Hall state is that I have to have an edge state. Okay? This is characteristic of a topological transition in space from one material of one topology to another of a different topology. There has to be an edge state of some sort. The gap that was present here has to close before it makes a new gap over here, because it has, if you like, it has the wrong symmetry. It has to invert. So the consequence of an edge state, which can be represented by a band like this. So here are the filled states, there are the empty states. This thing is the edge state that has to exist, and because the Fermi level cuts across the band gap, that edge state is always metallic. It's always conducting, okay, because it has to cross the Fermi level. If you look at the semi-classical picture of an edge state, it looks something like this. Inside the quantum Hall state insulator, you get orbits like so, cyclotron orbits, a charged particle in a magnetic field. But when you get to the edge, close enough that the orbit actually hits the edge, then what you get are skipping orbits. They skip along the edge here, and so the propagation of the charge is that way, that way, that way, that way. I have a chirality around the edge like so. And if I put some at the edge, in fact, it doesn't make any difference. In order for this electron to turn around and go the other way, to scatter and introduce resistance, what it would have to do is actually go all the way across this material. Okay? So the edge state propagating this way, in order to turn around, to be backscattered, it has to go all the way across the material. And that is incredibly improbable. And that's why the resistance, the longitudinal resistance in this state actually goes to 0. So this becomes a dissipationless state. Now there are of course details. If you look at the transverse resistance, it doesn't go to 0. In fact, it becomes quantized. Okay, and it becomes quantized essentially because this is a single mode, like a single mode waveguide. It has a characteristic impedance, which is characterized by the conductance or the resistance, conductance being E squared over H. Okay. So have these things been seen? Well, in fact, they have. Those, I back up a second. So this was the quantum Hall state. And that's great, except it does require a relatively high magnetic field in order to create it. It's kind of inconvenient for devices. Well, along comes topological insulators, two-dimensional topological insulators. The concept for this was actually came from Charlie Kane and Jean Millet at University of Pennsylvania. They were looking at graphene, but they introduced, in fact, they actually made a mistake in the original paper. They had spin-orbit coupling that was too large. But they realized some key things about that system, some key topological aspects of that system. And so the graphene played a really important role in developing this concept of two-dimensional topological insulators, also called quantum spin Hall insulators. These were first realized in a 2-6 system, cad telluride, merc telluride, cad telluride. So this is a quantum well. And if you make the quantum well thin enough, then what happens is that the hole states and the electron states, the discrete hole and electron states confined in the quantum well, actually invert. So the hole states go above the electron states, like so. And that inversion has to be undone when you get to the edges. And so undoing that gives you, again, an edge state, which is in fact a topological edge state. So at the edges, you find modes where, in fact, due to the spin-orbit coupling, so I didn't mention, but when you invert these states, it also inverts the sense of the spin-orbit coupling. And what does spin-orbit coupling do? Well, it couples spin to orbit. It couples K to the spin direction, okay? And so the net result is that these edge states, if they're propagating in this direction, then they're spin up. If they're propagating in this direction on this edge, then they're spin down. On the other edge, it's reversed. So again, if I want to take a spin up electron that's propagating in this direction and backscatter it to go the other way, well, either I have to flip the spin to get here. I can't do that unless I have magnetic impurities in the system. I need a way to transfer angular momentum. Basically, I need a magnetic impurity to do that scattering. So it doesn't happen in the clean system. In order to backscatter, this one would have to go all the way across here again. And again, I get then a dissipationless edge state, and I get the same for the opposite spin. But now I've got two on one edge. Okay? And so if you look at the quantized resistance of this thing, quantized conductance, it becomes 2 times E squared over H, because I have, going in one direction, I have 2 modes. They're on opposite sides of the sample, but I have 2 modes. Okay? So the two-dimensional topological insulators, or quantum spin Hall insulators, they also have these edge modes. There is a topological invariant, which is different from a conventional insulator or vacuum, and therefore these edge modes have to be there. Okay? They have to occur. The band structure of this looks like so. Now I have 2 states, one with spin up, one with spin down. And it's metallic because the Fermi level has to cross those states. It's really sort of a half metal because spin up and spin down are not doing the same thing. Okay, so in this band, I don't have both spin up and spin down. I've just got spin up. In this band, I've only got spin down. Okay. So these are still, the edge states, as I explained, they're still protected from backscattering for the reasons I said. Now, in 3 dimensions, if I have a 3-dimensional insulator, then things get slightly more complicated. There is a topological invariant again, and just think of it as if I have a 3-dimensional insulator, then the gap, if the gap has surface states, okay, states that live only on the surface of the 3-dimensional insulator, they might look like this, where they have to be 0 at k equals 0 because of Cramer's degeneracy. This is a fundamental theorem that says time-reversed states have to be degenerate. In most non-magnetic materials, that means just that spin up and spin down are degenerate. Okay? But in a material that has spin-orbit splitting, spin-orbit interaction, then I could have spin up and spin down being different energies. If I haven't drawn minus k here, but if I look to minus k, what would happen is I would see the mirror image of these bands and the spins would be inverted. Okay? So to do time reversal, I have to go to minus k, change the momentum, and basically flip the spin. Okay? What that means is that if I have a point like k equal to 0, where k is equal to minus k, then at that point, all I've got left is the spin flip, okay? That means that at that point in k-space, spin up and spin down have to be degenerate, okay? So that's the Kramers degeneracy requires that. Also, for a periodic crystal at k equals pi over a in this one-dimensional case, then out here also, because plus and minus pi over a, which I should have shown but didn't, they are degenerate. I also have to close the gap, or I have to have spin up, spin down degenerate at that point also. Now, if I do it like this, so that I have an even number of crossings of the Fermi energy, then in fact, if I were to distort this thing, move these in energies, I could arrange to have the Fermi energy coming at a place completely between the bands, and I could still have a gap. This would be a trivial or normal insulator, okay? But you could have a case which would correspond to a different value of this topological, called a Z2 topological invariant. You could have a case where I get an odd number of band crossings. And in that case, I'm stuck. If there are an odd number of crossings of the Fermi energy, then in fact, I have to have a metallic surface state, okay? That's this case over here. Again, I have to have degeneracy, the Kramers degeneracy here at k equal to 0. That's gamma A is k equal to 0. And I have to have it also at pi over a, okay? So that's what happens in a three-dimensional topological insulator. In the two-dimensional topological insulator, we have these edge states. In a 3D topological insulator, we have these surface states. The surface states have a defined relation between the k and the spin direction, okay? So if k direction, the direction of propagation of the electron changes from this way to that way, then the spin goes with it, okay? And because of that, again, a backscattering event would not have to just reverse k, it would also have to reverse the spin, and that is dramatically inhibited unless you have magnetic impurities, okay, or a magnetic field. So these, these surface states appear really, really interesting just from the perspective of devices, because potentially we have this protection against backscattering. And in fact, it goes further than that. It's really protection of the quantum state itself. So, how might one think about using these new concepts, which really only started taking hold? Kane and Melia was 2005 or so, but it has rapidly grown. You can think about, well, using those, I mean, here are the things that are good. You have dissipationless edge states, or in fact, if you have magnetic materials, you put a magnetic material here and there, you can open a gap, because now I can transfer angular momentum. That's one thing a magnetic material can do. And so I can open a gap here and I can open a gap there, and the sense of those gaps is reversed. It's like changing the mass from positive to negative effective mass. And in between, you get a required chiral state that will go down that channel, and it will be dissipationless, okay? So that's something that one could use for transmitting information. And in fact, you could transmit spin information, right? So these, we're dealing with the spin of the material, and so if one wants to do spintronics, have devices where the computational variable depends on the spin orientation, you could potentially do it with these sorts of materials. And there have been, so I put this here because it's an FET, and everybody loves to see an FET. If you have an FET with a ferromagnetic insulator here on top of a topological insulator, you can use this to do actually very effective switching. But the thing that lots of physicists are really, really gassed about is the possibility of doing topological quantum computation. So these states, quantum states, they have topological protection. Topological protection from environmental decoherence. So for years and years, what we have done is we have used the electronic structure of materials, basically drift and diffusion, to make currents flow. We charge up capacitors. There's a charge there that's a bit 1. There's no charge there. It's a bit equal to 0. And that's taken us a long, long ways, but there's dissipation there all the time just by virtue of charging the capacitor up and taking the charge off. There's a prospect out there called quantum computation, for which the ones and zeros basically are quantum states, and in order to do computations, one has to entangle these quantum states. It's like creating a singlet out of two spins. That's an entangled state, okay? Or a triplet out of two spins. So I won't go into any of those details, but the problem with quantum computation is that quantum states are sort of inherently delicate. You know, you rely on phase differences. You know, if I have a Fabry-Perot interferometer and I just jiggle the mirrors a little bit, it just doesn't give me maxima any longer, right? Same is true with quantum states. If I start jiggling things a little bit, then I decohere. But if I can arrange to have the quantum variable a topological variable, then a little bit of jiggle over here has to be compensated somewhere else so that basically an integral becomes a constant. It's a little bit like Gauss's law. It has to give you always the charge that's inside, or the Cauchy theorem, which says that you go around a pole in the complex plane and you have to get a particular number, right? It's the same idea. If you can have your computations rely on pure numbers like that, then in fact you can have protection from this decoherence and potentially implement a topological quantum computer. And so the computation would be an entanglement of these quantum systems, and I better shut up before I get too far beyond what I know. Great, here's what I do. I don't do that. I do measure things, though. So how do you measure those interesting bands, interesting band structure in these new materials that have what I believe is great potential for devices? Maybe it's 30 years down the road, but it's great. How do you measure them? Well, the standard way to measure electronic band structure is angle-resolved photoelectron emission spectroscopy, ARPES. Okay? And these bands that you see, this is energy as a function of a slice through k-space, through momentum space, that shows the Dirac cone for a particular topological insulator material. And if you measure around here, what you see, this was spin-resolved photoelectron emission, you find that the spin direction also changes around that cone. And so the structure near the Dirac cone looks kind of like this. The spin direction is connected. It's perpendicular, effectively, to the k direction. That gives you a chirality up here and the opposite chirality for states down there. Great. Well, ARPES is wonderful, but it's a macroscopic technique. So what if you want to make nanostructures? Because getting this high density of things to make CPUs, etc., it's still very, very valuable. So what about nanoscale techniques? Well, there is a nanoscale technique out there. It's called scanning tunneling microscopy. You can also do atomic force microscopy. Really, both of these down to the atomic scale these days. And so we have in the past studied graphene a great deal, looking at the arrangement of atoms in islands that occur during growth of epitaxial graphene. And I won't go into details. We've looked at, this is my favorite defect. This is a flower defect that we discovered, actually experimentally discovered it quite a while ago, but it took a long time to get the theory right. And this is a density functional calculation done by Eric Cockayne at NIST. And what he found was that this flower defect is in fact perfect graphene, but in the middle you take these 7 hexagons and you rotate them by 30 degrees and then connect them back up. And when you connect them back up, you get 7-fold, 5-fold, 7-fold, 5-fold pairs, which can be viewed as each one the core of a dislocation. And so this, this grain boundary is sort of, it turns out to be incredibly low energy to form and just really interesting. More will happen, I'm sure of it. So how do we take that technique, scanning tunneling microscopy, and I say scanning tunneling microscopy because it directly looks at electrons as opposed to atomic force microscopy, which is forces. So if we're looking at electrons, can we get the electron density of states? Or because it's an imaging technique. It's the local density of states, the LDOS, that we're going to be interested in. So the local density of states can be a function of position, of energy, also the magnetic field if we choose to turn on a magnetic field. Now these experiments are done at 4 Kelvin, and with the magnetic field we went to NIST, where a colleague of mine, Joe Strozio, has a wonderful instrument for going to high magnetic fields. Let me just give you an inkling of what goes on. If you have a spectrum, so this is the differential tunneling conductance, DIDV. This happens to be in a magnetic field, but if I show you a map like this, that I call a local density of states map, or DIDV map, what it is one energy. So here I show the average spectrum averaged over all positions on this surface. We have taken 100 by 100 spectra on this surface, so at every one of these XY points there's a spectrum like this, okay? And we take one energy and we display it as a map, like so. And if you're on this peak, it happens to look like so, where the dark is low density of states and light is high density of states. So the first method that I'd like to point out is that one can use is to use point defects that might occur in a material that as themselves band structure probes, okay? And the way you do that is, well, first make a little model. These are point defects in a material, and let me just pretend I have waves in 2 dimensions that are scattering from them, and then I get a nodal structure due to interference of those waves. And if I change the wavelength of the waves, the nodal structure changes. Change the wavelength again, the nodal structure changes. And of course, changing the wavelength is changing the electron energy. So those standing wave patterns, this is the standing wave pattern. It's the wave function on the surface due to all the interferences that occur from scattering from these defects. They depend on energy. And this is how it works. Over on the right-hand side here, from red to purple, I'm denoting the energy. And so if I let this go, the color denotes the energy. It's crossing the Fermi energy around now, and then goes back up to high energy, and it's going to start over again down here. What you're looking at is 100 by 100 angstrom area, and these are slices at different energies. So this is psi squared, the wave function squared, or the electron density as a function of position across the surface. And all these dark things moving around, that's the nodal structure of those waves scattering on the surface, the electron waves, okay? And you might think, well, those dots there, those are atoms in the graphene, but it turns out that they're not exactly atoms in the graphene. Here's the topography. So you can see the atoms, the atomic structure. The structure there is not exactly the same. And it's not the same because these really are the standing wave patterns that we're seeing. They're created by having electrons near the Dirac points. This is the close-up of that energy structure again. Take a slice across here. So an electron at this energy, if it's elastic scattering, has to stay on that circle. And so it can scatter to any one of these other points on the circle. But the place it does it most is right across the circle where the regions are sort of parallel to one another, because that has the most connecting vectors, nesting vectors. So the nesting vectors basically are Q1 and Q2 in this system. And if I take a Fourier transform of the data that I showed you as images, as XY images, the Fourier transform might look something like this. It does look something like this. It is that. And if you do that at many different energies, you can get out the Q vectors, or the K vectors, if I sort of just multiply by 2, if you look at the previous thing. And you see this line. That line, in fact, is the edge of the Dirac cone. And what we discovered was that this didn't go down to the Dirac point. In fact, the Fermi energy lay about 300 millivolts above the Dirac cone. That meant we have N-type doping in the material. Okay. And that kind of looked like noisy data, but I'd point out that if you take that, which was taken over 100 angstrom area, and compare it to ARPES, in fact, it's actually pretty darn good in terms of the K resolution and, in fact, the energy resolution, and you can get empty states as well as filled states. Okay, so here's one way to measure electronic structure down on the 10 nanometer sort of scale. If you have a magnetic field available, and we did, that would go to about 8 Tesla, then you can start studying things with even better K resolution. So the sample that I'm going to tell you about is graphene, which is stacked in this manner. It has twists, little rotations between layers. Happens to be the way it grows on top of silicon carbide in a particular fashion. If you zoom in, you can see this is the atomic structure, so this is the graphene lattice, but that little modulation is a consequence of the moire pattern that occurs due to the interference of the crystal structure of one layer on top of the other. And that's what I've tried to denote here with the yellow and red and the blue and blue. There actually, we see two structures here, so we know that we have at least 3 rotated layers. It's a double moire structure. The effect of that is to remove overlaps from one layer to the other between PZ orbitals in one layer to PZ orbitals in the next layer. That decouples, has electronic decoupling of the materials, and as a consequence, I'll show you that the electronic density of states looks a lot like single layer graphene, but what we're studying is the top layer on a stack of about 10 of these rotated layers. Okay? So I better not spend too much time, but just if I look at the density of states as a function of energy and magnetic field, these quantized orbits, the cyclotron orbits in the material, they're quantized essentially because I have to have the wave function wrap back onto itself. Gives me discrete energies then, because I need an integer number of wavelengths around the circle. It gives me discrete energies, and they all depend on the magnetic field. So that's what this dispersion is, that as I increase the magnetic field, the spacing between these states gets larger and larger, and the intensity of this is the density of states. Okay. If I take a cut through that, I see a density of states picture that looks like this, and the significant thing about graphene is that it has a peak at 0 energy, and that does not disperse with magnetic field. That's a consequence of the topology of the graphene band structure itself. And the other thing is that because of the linear dispersion instead of normal parabolic dispersion for energy is p squared over 2m, I get something which the spacing of these peaks depends on the square root of this orbital index and the square root of magnetic field. That's in contrast to a normal 2D electron gas that has normal parabolic electron dispersion. So what we find is that, in fact, we can stop on the surface of the sample. We can take a spectrum like this, sweep the voltage between the tip and the sample, and look at the derivative of that, actually using locking techniques, and we see these beautiful peaks. And if you plot them as a function of this or in that functional form, what you find is that, in fact, they obey that functional form very, very well. And if I go to many different magnetic fields, they obey that functional form extremely well. And, in fact, you can then measure the slope of the band structure, measure the band structure itself. So that was basically measuring this slope. We can take a different cut, obviously. It's not that obvious. Experimentally, there are issues. This experiment where I sweep the magnetic field has to be done in closed loop so that the tip is always tunneling to the surface, because when you change the magnetic field, things move a bit. And you don't want to crash the tip into the surface. So this cut, though, actually allows you to get information at a lower magnetic field than was necessary for getting those discrete peaks that I showed you. These are analogous, these oscillations that you see in the magnetoconductance, that's the DIDV, as a function of magnetic field. They're analogous, for those of you who know, to Shubnikov de Haas oscillations. It's a conventional means for measuring Fermi surfaces. And from the period, or the period in 1 over magnetic field, you can actually get the area of those discrete states in k-space. You can find the k-space orbit. And the result is that we get the Dirac cone, and compared to the best ARPES resolution, it's actually really, really good, both in energy and momentum. We didn't get very close to the Dirac point because, as I said, we have to do this in a closed loop manner, and we don't want to crash our tip. So that's another great way to get local electronic structure information, but I haven't shown you any mapping, okay? Mapping the surface means take the electronic structure information as a function of position and find out what's going on. So here we are using the magnetic field again to look at the spatial distribution of Landau level energies. And so I'm going to show you maps at different energies, and they apparently I'm not going to show you. Wait a second. I am going to show you, if I remember how to do it. Is it still going? No. Okay. So this is just sweeping to different energies. And every time it goes over this peak, these quantized states, okay? So this is the average spectrum. It sweeps over the state, and you see this enormous spread in the density of states. It spans the entire sample. But before it spans the entire sample, if you look very carefully in these lower areas, you'll start to see these rings going on, and you'll start seeing rings develop in here as it goes up the edge of this Landau level. Rings, 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 rings. They're ring, more rings. And then the rings sort of invert. They become dark and go on the downside, okay, until it becomes black. What you're seeing is, again, the distribution of Landau levels on the surface. And if I look at an energy that's below the mean of the Landau level, I see a ring like this. And what's going on is that I get a cyclotron orbit that's going around like this. It's very, very small, and it's circling on an equipotential, okay? And if I go above the Landau level, I get things that circle equipotentials that are rises in the surface. If I stick right on top of the Landau level mean energy, I see this distributed all across the sample. In fact, it is these states that destroy the quantum Hall dissipationless state and quantized Hall conductance. And they destroy it because this state, through this state, I can couple one edge to another. And I have a topological transition from basically one edge state to two edge states to three, etc. Okay. Those localized states look something like this. The rings, they have the cyclotron orbit that just drifts around an equipotential, and so that localizes these states in energy. That's what keeps the bulk, the middle of the sample, insulating. And if I look at the average Landau level, that's energies over here. But if I take the STM looks locally, and it sees only a Landau level that has a shifted energy because the potential of the surface is a little bit different. So this gives us a way to actually measure potentials on the surface. And if I look around a bump in the surface potential, I see the energy of the local Landau level up here. And again, at the average energy, I get this thing running along lines, which connects one side of the sample to the other. Now, when we did this work, we actually sort of expected to see those types of features. What we didn't expect is that in some regions, we found a dramatic atomic scale change in the Landau level energy. So as we went from one point to another, the Landau level energy changed by tens of millielectron volts, which for these temperatures was a big energy. So what we were seeing was spatially, there's a gap here in energy between these peaks, which I'll label A and B. And over here, at a different point on the surface, there was no gap. That gap is a consequence, in the end, of having some kind of symmetry breaking. And the symmetry breaking that goes on is that when you have this moire between the two layers, you find that you get regions where things line up very well. You get other regions where A atoms on the top surface align with B atoms on the bottom surface. And then if you go to another spot, you'll find B atoms on the top surface aligning with A atoms on the bottom surface. That AB to BA transition, in fact, changes the sense of A and B. The overlap of the atoms from one layer to the next gives us a gap, an energy gap. And so locally, what you find, if I plot the splitting as a function of position, you find these patches where there are energy gaps. And those energy gaps are a consequence of this coherence, the alignment of A and AB or BA And if you think about it, this dark region in between, in fact, is where you have a transition from blue here, green there, to blue here, green there. And that transition, in fact, is equivalent to looking at positive effective mass, negative effective mass, right? Holes have negative effective mass, electrons have positive effective mass. But here I change the sense of which is which by changing the sense of the A and the B atoms. So effectively I have a pattern effective mass that goes from positive to negative, and in between, in these little lines that go in between, then in fact you would expect that in these dark regions there is actually a topologically required state, a band crossing in graphene itself. Marcus Kinderman is responsible for most of the theory of that. And I got to wind up. Ooh, I do. Always pay for technical mistakes. Let me show you a little bit about what's going on here in Walter's facility, the materials characterization facility, where we have installed not so long ago low temperature scanning tunneling microscope and atomic force microscope that I dearly hope becomes a facility for the campus. Now these measurements are not easy, they're time consuming, but I think they're worth it in many cases, especially for these types of materials. So we are studying, for instance, hafnium pentatelluride, where we see atomic rows. These are double rows of tellurium atoms, and in between, in these blue regions, there are sort of double zigzags, which I don't show you on this picture. And there are some dopant atoms in here which appear with a slightly modified height. It's about 1 angstrom from top to in height scale that you're seeing here. The graphene that I showed you, largely the height scales that we're dealing with were tens of picometers. I'll remind you that the Bohr radius is 50 picometers, right? So these vertical scales are typically on the scale of a hydrogen atom or less. This is zirconium pentatelluride. We're trying to compare these things to find out whether on one we have a three-dimensional topological insulator, and the other we might have just sheets of two-dimensional topological insulators. Here's the image of a defect in the material. These results are due to Di Chen, who works for Zhigang Zhang and myself. Now, how do you start mapping these densities of states again? So this is the density of states. It is dIdV normalized in a sort of standard way. Here's where the Fermi level is at zero bias. The chemical potential of the tip and the sample are equal. Now, I have not taken the time to show things quite as fancy as previously, but what we try to find out is where are the empty states and where are the filled states on the sample. So if I look at the blue areas, those are the filled states, that is, states below the Fermi energy, and I'm tunneling at a bias out here, so I'm sensitive to all those filled states. If I tunnel at a bias out here, I'm sensitive to all these empty states in the current flow, and where both of them overlap is where it's white. Okay, so I color red for the empty and cyan for the filled states, and the overlap is white. So we are trying to decipher some of this stuff. This sort of thing, again, this is acquired downstairs. This is a map. I didn't label. This is 7.5 nanometers on a side. And these are the double rows. Okay, we're going through this area right now. This is what I didn't show you is the guide bar, right? But where everything vanishes, that's in the vicinity of the Fermi energy. Otherwise, we're going this way, and then we're ping-ponging back and forth like that. Okay? And so what D is trying to figure out these days is exactly where are the filled states, where are the empty states. It matters because then we can compare to a band structure calculation and not only look for the energies, but is this a tellurium in the zigzag range, or is this a tellurium in the dimer rows? And those determine the symmetries of those states when we compare to a band structure calculation, for instance. And we're also trying to determine whether there are states living within this band gap. Finally, the last thing I'll say, that the capabilities of this instrument, that it's right under your feet, are such that we can mount a tuning fork quartz crystal tuning fork known as a Q+ sensor. This is for doing atomic force microscopy. And our goal, which is at the moment funded through the campus EFRC through a seed program, our goal is to measure, do molecular imaging of the surface of a metal organic framework used for sucking up acid gases from the atmosphere and other places. So our goal is to do this on these important materials for chemical engineering. Okay, this is real bond scale imaging with the atomic force microscope, where you put a CO molecule on the end, and this is not our work, not yet. I'll thank collaborators over several years. Zhigang Zhang is the one who's really spearheading the topological insulator work, and Walt DeHeer, Ed Conrad, Claire Berger, and I have collaborated for quite a while with Marcus Kinderman for graphene work. Joe Strozio has been a great friend for helping us with some of the STM stuff that I've showed you. Thank you.
Questions from the audience?
Yeah.
One in the back there.
The strips that I showed were part of the crystal structure. I didn't show you the crystal structure. The strips that you saw in the movie were these strips. They're dimers. They're tellurium dimers. Okay. They live on top of the zirconium in this case, covering it all up, in fact. Yeah, the surface states would live in here. In fact, we think that this may be a surface state. We are in the midst of comparing some of these things to infrared results that Zhigang Zhang has done, as well as some band structure calculations to figure it out for sure. What we do find is that when we do get close to a step edge, so these materials they're layers of atoms, right? When you get close to a step edge where I have n+1 layers here and n layers there, you do see a change in the density of states, in particular in this region. And that may be a sign of a topological edge state at the step edge on the surface. Okay. So there may be interesting things that one can do to play with those things from a device perspective. If you take a crystal and you create it at a miscut angle, so then you have an array of these conducting lines, then start connecting them, etc.
So you've shown that zero energy state as the intersection of two cones, but graphically it looked like it was represented as the intersection of two hyperbolas. In fact, you reference a saddle. Is one just an approximation, or is it actually a cone?
So in the case of when I talked about the saddle, that was with a magnetic field applied. Okay. When you apply magnetic field, the band structure changes into these quantized states, where K is actually no longer strictly a good quantum number, but the orbit number is, and the size of that K space orbit is determined by the magnitude of the wave vector. Okay, so that in that case, the cone was still there. Now, and in graphene and in the topological insulators, it really is a cone. It's a crossing. Okay. Now, it doesn't have to occur in the topological insulators. It doesn't have to occur at the charge neutrality point, but it has to be there in the gap. Okay. And if you get something that is hyperbolic, as I did show when I had the multi-layer, then it means that you have broken one of the fundamental symmetries somehow. Or in the case of the topological insulator, when I applied a magnetic field, it could break that symmetry when I put magnetic materials on top. And in that case, you can get a gap. And the gap essentially has a sign, a parity associated with it depending on, in the case of the magnetic field, whether I broke it with magnetic field up or magnetic field down. Okay. And then you can get more fun topological things when you have a transition from a region where magnetic field is up to a region where it's down.
Well, I was wondering in the middle when you were talking about the spin states and changing them, the time frame for this, how rapid can this be made to happen? Is that an issue?
I don't know. I mean, in conventional magnetic materials, you can flip things pretty fast, in fact. But it is always it depends on how big things are and, shape anisotropies and things like that. So it may, in this case, I would guess it actually depends more on what you're using to drive the spin flip. Okay, so to drive the spin flip, you're going to yourself flip something like an external, the magnetization in a magnetic bit, for instance. And I think that will be the determining factor is flipping that domain, not so much the in the material itself. But honestly, I don't know the detailed answer, but that's my gut feeling. Now, magnetic random access memory, for instance, I'm pretty sure can operate at the same sort of speeds or even faster than conventional DRAM sort of memory, if that is relevant to anything.
But I guess you would have to find a way to do this which doesn't rely upon a conventional way to do a stimulus.
It doesn't rely on charge, for instance. Yeah. So there are very interesting possibilities for that, like the spin torque, for instance. And so if you drive a spin polarized current into a magnetic material, you're driving a continuous torque that can flip the magnetization of that material. That approach, so far, it's not lower energy than other things. So yeah, there's work to be done. Eric.
As a follow-on, has anybody measured decoherence times in these materials at anything above 4 phase?
Let's see. So yeah, so decoherence is going to depend on the sort of scattering that I talked about, where you have to turn things around, also on energy scales. So in order to isolate in energy, you would typically need a gap of some sort. And I don't know the answer, unfortunately. I know that in graphene, for instance, the quantum Hall effect, which requires essentially coherence of the edge state right across the sample, that's been seen at room temperature, and in fact is now really I don't know how far it's gotten, but it's going to become a standard, basically a transferable standard from NIST and other places for resistance without liquid helium, which is $16 a liter.
Well, if there are other questions, I think Phil will be here, and certainly to put in a plug for his work and for our center, as he said, we have really maybe not quite state-of-the-art, but certainly a really capable system downstairs.
This work was done on an instrument which was essentially the same.
Okay. So then and he's glad to talk about collaborations. I'm glad to sort of answer any questions about that. We both want it to be a resource for campus overall. So please hit him up or hit me up for some information. And let's thank him again.